Today we're going to be having a look at high efficiency transference of electric power. We're going to be using the cylindrical Tesla coil system I've already posted a few posts on my website relating to these particular coils and geometry, the design, and also a detailed analysis of Z11, the small signal input impedance. Now we're going to do a transference of electric power experiment. This is a high efficiency experiment and demonstrates very well what's capable with this type of coil geometry in a TMT system. So what we've got set up at the moment, we've just got one coil connected, and there are actually two. I'll just pan around so you can have a look and see what the overall experiment looks like. Okay, there's the receiver coil. There's obviously also there some 500 watts, a pair of 500 watts incandescent lamps, which we're going to use as a load at the receiver. There's also a power meter there. I'm going to come back to that setup in just a minute. Okay, so if we come back round to the experiment, just a little bit further. Shall we get everything in? Okay, so we're going to be using the linear amplifier generator to drive this. This allows us to drive this at a single frequency, which we can control. And I'm going to be going through the overall setup of the linear amplifier, and also how to do the tuning, how to get the matching right, and ultimately how to drive this system for transference of electric power experiments. And then we're going to be doing a range of different experiments to look at the characteristics of the system. But just to now go through the overall system. So the linear amplifier starts from here, from an exciter unit. This is a Kenwood TS430S radio amateur transceiver. It's from the 1980s era, which makes it particularly flexible. It's at a time when it was all mainly discrete components, built on discrete components, although it does have digital synthesis, so it makes the frequency control quite accurate. And there's a lot of modifications and additional things that you can do with this transceiver. I particularly like Kenwood. It's well made. There's very good documentation. They are relatively easy to service in this area yourself if you're electronically minded. So I've got several Kenwood pieces. The linear amplifier is also Kenwood. I'll come on to that in a minute. Now, this transceiver has been modified so that it can transmit over all frequencies. So it has quite a wide band. This is an HF transceiver, and it has a receive band from right down from 10 kilohertz all the way up to 30 megahertz. And it can be modified internally so that it will transmit over that entire band, not just in the amateur bands. And that makes it a high power benchtop signal generator, 100 watts. It's also been a little bit tweaked, so you can get about 120 watts out of this in band, in most bands. And obviously it has all the normal things that amateur radio comes with, so it's AM modulation, FM modulation. It makes for a very good high power exciter that you can use to drive a number of things. And I'm also going to demonstrate how we can actually do the experiments just using this exciter. It's surprising how much you can do with 100 watts, and I'm going to be demonstrating that as well as part of this video experiment. But also, if we want to go higher power, then we need a linear amplifier. This is a Kenwood TL922. It's also from a very similar era. It's a vacuum tube, final stage vacuum tube based linear amplifier. It's got dual 3500Z IMAC tubes. Very robust, very well made. This also, it should be noted that this has got Pi network matching both at the input and the output. So when working slightly out of band, then we would not necessarily expect to get all the gain out of this linear amplifier. This is good up to 1 kilowatt, obviously into a matched load. It's a nominally 50 ohm system impedance, and we're going to be looking at how to set up, get this all matched, and then run the experiment, taking into account all the things that need to be done so that the linear amplifier is happy with the matching, and we're not getting large reflections back from the experiment. And that's particularly important when we want to do high efficiency experiments. We don't want that power reflected back from the circuit. We want it to go all the way through the transmit side, all the way down the single wire of the TMT system, and then out into the receiver, and obviously in whatever load we've got coupled on to the end of the receiver. Okay, so the signal goes from the exciter to the linear amplifier. The linear amplifier can operate in standby or operate mode. So in standby, it means the signal is just passed through. Although the linear amplifier is on and the valve tubes are warmed up, it's not actually doing any amplification. Only when we switch over to operate will the linear amplifier amplify the signal coming from the exciter. So we can use it in both modes. The linear amplifier is connected directly to the output of a digital SWR and wattmeter, that's standing wave ratio, and this is important because we need to determine here the standing wave ratio that the linear amplifier sees into the experiment. And obviously this linear amplifier is designed to work best the closer you get to a standing wave ratio of 1, where 1 is a perfect match to the system impedance, which would be 50 ohms. This is an MFJ 826B. I like the digital readout. It combines both analog and digital in that it has an SWR bar that moves over here, and it shows the frequency, it shows the power out, and digitally the SWR as well. So you can see everything all on one screen, and I find that particularly useful when I'm doing the tuning. So through the output of the SWR and wattmeter, then we have a PowerStar 85K antenna tuner. This is a 5 kilowatt antenna tuner. This is particularly important because this is what's going to do our impedance transformation from the 50 ohm system impedance of the linear amplifier into the low series resistance, which is presented at the fundamental series resonant mode in the primary of the Tesla coil. Remember, that represents a transformed down impedance of the secondary at resonance, plus any additional circuit elements, reactive elements and resistive elements presented by the primary at that point. So we are going to be driving this. This system is suitable for driving a Tesla coil or TMT system at the series resonant modes. For more information on those, for the series and the parallel modes, there is a post on my website which covers these things in a lot of detail. And we're going to be using some of that information and that data in order to set ourselves up. So going back to here, this shows obviously the forward power and the reflected power. This is a double needle gauge, and they both go up as we put power into the system. We have continuously variable input tuning for this is a T network tuner, so it has an input capacitor, it has an output capacitor, and it has a roller inductor. And by tuning those three elements, we can match the output of the linear amplifier to the experiment, and that way we can get maximum power transfer from the exciter and or the linear amplifier into the experiment itself. Now this also incorporates a 4-to-1 balun. We are using that here. So we have got it in tuned balanced mode. So in other words, there is a 4:1 impedance transformation going on at the back, as well as a tuning, which obviously also takes us from the unbalanced coaxial case to the balanced scenario, which is also important because we are driving a half wave primary coil, and we are driving that in a balanced mode. So without that, it would become very difficult to get the SWR down below about 3. But in this case, with this tuner, we are going to be able to get the SWR down very low, almost to 1, maybe even 1 in certain different tuning positions. Now, the antenna tuner allows us to go direct. So in other words, without being in the system, and also in a tuned mode. So this has also got a bypass, and the antenna tuner is connected to a PowerStar DL2K dummy load. That's a 50 ohm, 2 kilowatt peak, 600 watt continuous dummy load. And the importance of that is it allows us to tune up the output of the linear amplifier. The output of the linear amplifier has a pi tuning network, which is selected by band. Obviously, we're on the 160 meter ammeter band. We're going to be operating around about the 2 megacycle region. So the 160 ammeter radio band. And to do that, we need to tune the plate output from the tubes, and obviously the load output on the other side of the pi, which then obviously the next stage is through here and into the antenna tuner. So connecting to the 50 ohm dummy load is an important step to get the linear amplifier tuned up correctly, at least for a starting point anyway. We will have to retune this, and we will have to retune the output of that as we work with the experiment, especially as we push the powers up higher. Now, all of this equipment is also needs to be well grounded for this kind of experiment, and it has a network of grounding behind these instruments, and that connects to here. This is a 6 AWG silicon microstrand earth line, which goes to my dedicated RF earth, which I've got just outside the other side of the door here to the lab. And that keeps basically everything on an independent from the line supply earth. Important when we're doing RF work and tuning, that we keep everything stably earth from the equipment point of view. So the output from this antenna tuner comes out through a Bird through line wattmeter. This is a 4410A. It's got a 450 kilohertz to 2500 kilohertz 10 kilowatt slug in there, which is obviously is correct for the band that we're going to be working in, around about 2 megacycles, 2000 kilocycles, and that is our final measure of power going into the primary circuit, and we're going to be using that to look at our efficiencies in terms of the transference of electric power. Now, when I panned the camera around earlier, you also saw that there was a Bird, same Bird through line wattmeter, a 4410A, on the output of the experiment. It's got the same slug in it, 450 to 2500 kilocycles, and that's going to be measuring the power output actually coming out of the receiver and into the load. And that is going to be our measurement. We're going to use those measurements to actually determine our efficiency for the transference. And importantly, those Bird wattmeters were calibrated inline. So in other words, you put out a known amount of power, pass it through the first one, pass it through the second one, into a matched load, and then calibrate them simultaneously together. Then, of course, make sure that there's no connection losses, reverse them, and then check the calibration again. So because we're going to be using a ratio of the powers in those wattmeters, those have been carefully calibrated in line with each other. so against the same nominal input and output power. That really covers the overall setup of the system. What I've done prior to starting this experiment is just balanced the input using the primary tuning capacitor of the Tesla coil. So in other words, the adjustment here in order to balance the two parallel modes. First of all, we need to check the setup, and that starts with setting the correct frequency that we're going to drive the system at. Now, with a linear amplifier here, we're going to work at driving this system at its fundamental series resonant frequency. That is the frequency that you would measure if you were doing a simple resonant frequency test here. Now, obviously, if you're using a balanced antenna tuner, then you can also see the parallel modes in there as well, and I'm going to take a look at both of those. So first of all, we're going to have a look at the series resonant mode, the fundamental. So from the Z11 characteristics that we took, these are obviously on the page, but they show the kind of characteristics that we're looking at. We have three markers there. We have at M1 and M2 and M3. M1 and M3 are the parallel point resonant modes, and at marker 2 we have the fundamental series resonant mode. Now we're going to be driving, ultimately we're going to be driving this system at marker 2, but before that we're going to do some checks of this system. So we're going to measure the resonant frequency by another means, which will allow us to see the correspondence with the Z11 results, and to make sure that everything is a known starting point for where we start these experiments from. So first of all, I'm going to do straightforward series resonant frequency test. So I'm going to put this onto, so the antenna tuner is not involved in the process, and it's just bypassing. So it's not bypassing to the dummy load, it's just coming, the exciter's going through the linear amplifier, the linear amplifier is on standby, so it's just passing through into the antenna tuner, and the antenna tuner is just passing it to the output of coax 1. I've got coax 1 connected through the power meter into the experiment. So by adjusting the frequency on the exciter, we will be able to see, using an oscilloscope, what we get at the output through the secondary circuit. So to do that, I'm going to put a oscilloscope on here. I'm going to attach the input to the oscilloscope, not actually physically attached to the top end of the secondary coil, as that would actually cause loading of the secondary coil, which would then also change the resonant frequency characteristics that we were measuring. I'll just point that a little bit towards the camera so we can see. I'm going to be adjusting frequency here on the exciter, and we're going to be looking at the output on the oscilloscope. So I'm going to zoom in a little bit on the oscilloscope so we can see the kind of measurements that we're taking. Should be enough. See all the details. Okay, so I'm going to turn the exciter on, minimum power, and immediately we can see we're at 2 megacycles, 22.1 volts RMS coming out from the top end of the secondary coil, and I'm going to adjust the frequency now. I'm going to go down first of all. We can see that's reducing. 1.9, going down. 1.8. So it's just falling away. So if we're moving away from resonance there. So I'm going to start winding back up again. 1.7, 1.8, 1.9, sine wave increasing, 2 megacycles, going up, growing quite big now. 2.09, almost full screen, just go up a range. No, this one, that's it. And we're peaking about there. And if we go past the peak, starting to collapse. Starting to collapse. No sign on this direct drive of the parallel modes. Just that central series mode at M2. That jump there was the exciter switching bands. Come back up. We're going to find that peak point. About there. Just going to set that accurately on the exciter and lock it to there. 2.14 megacycles. Now on our Z11 we measured 2.19 megacycles, so not exact. We might expect that given our system setup is slightly different. Cabling, slightly different positions, slightly different tuning, but very close correspondence. 2.14 megacycles, 2.19 on Z11, and that is now tuned. The system is now tuned to the correct frequency for driving this system at the fundamental series resonant mode. Before we do that, I'm going to switch over to the balanced. So the antenna tuner is coming in, so we can explore what Z11 looks like from that perspective. So I'll unlock the exciter again. I'm going to switch over to the balanced mode. I will just need to change the wire output for the balanced mode. Okay, reconnect the balanced mode. I've got the antenna tuner set to balance now. I'm going to turn the exciter on. Once again, we were at 2.14 megacycles. I haven't changed the exciter. Actually quite a bit smaller output now. Let me first of all go down. Collapsing, collapsing, hardly any output at all. And here now we're starting 1.2, 1.98, starting to go through a peak. There, it's not quite as large a peak as the serial, but almost. There, 1.89. Have a look. So 1.89 was marker 1. It's our lower parallel mode resonant frequency. Now we're driving it in a balanced mode. So we see how the impedance actually looks when we've got it matched. Going to go up a range there. 2.03, 2.07, rapidly coming up. It's our series mode. Going through a peak there. 2.22. That's our series mode, 2.21. We had 2.19. Carry on going up, that'll collapse away. Start diminishing. Now it starts coming up again. Right up to there, seems to be about the peak. And that is marker 3, or the upper parallel resonant mode, at 2.68. There's an exact correspondence there. So we're driving it through the balanced mode, and now we are seeing what Z11 actually looks like. Whereas before we were driving it just without the antenna tuner in there, without any state of tune, we were just driving it straight with the connection of the exciter directly fed through. And what we were seeing in that mismatch state is only the fundamental series resonance as a peak. Now we're seeing all three, 2 parallel modes and the series mode. If I carry on up from there, it's going to fall right off now, up to 3 megacycles, come all the way up, there we go, through the upper parallel mode, dropping down, now coming up, as we come, starting to rise again as we come to the fundamental series mode, around about there, 2.21, 2.22. That corresponded very nicely with the previous Z11 measurements that we made that I put on the post to the website. I think the balance point there actually was 2.22. Can carry on down. That's right away. Starts rising up again towards the fundamental parallel. It's quite large. It's got off the scale. Just go up a stage. There we are. 1.89. 1.89 on the Z11. So very good correspondence now that we're running in balanced and tuned mode. So in other words, the exciter now sees a matched scenario, and we can see all of those characteristic impedances, 3 characteristic impedances of a Tesla coil, where the primary coil is coupled together with the secondary coil. So I'm going to tune back now. Back to our fundamental series mode in the measure, which is where we're going to drive this system for maximum transference of electric power. Right in the middle. We do that because we want to excite all of the modes, and it also represents the lowest series resistance, which, for example, if we're driving with a discharge-based generator like a SmartCap generator or something, we want to really minimise that impedance or that series resistance of the primary at the resonant point. We go back to where we find that peak. It's about there. 2.2. Lock that into position. I will just come out from the camera and show them what I've done there. So if I just pan the camera out, come back round to the experiments, get everything in properly. Gets everything in. We can take away this now. Done the work we needed to on that. And we can see now here what I've got set. I've got that set to 2.2 megacycles and I've locked it in place so that doesn't move. And that's pretty important because characteristic of this system using a linear amplifier generator, when you're running at power or higher power, you cannot just adjust the frequency over quite large ranges because you are changing the tuning considerably, and that will affect ultimately the SWR of the system and the amount of reflected power coming back to the linear amplifier or the exciter. So really the mechanism here is to set the frequency that you want, tune, wind up with power, gradually tuning, making sure that SWR remains low, and if you want to move to another frequency, then wind it back down in power, readjust the frequency, and then wind up doing the tuning. And we're going to see how that works during this experiment. So we've made a check of frequency both for the balanced and the unbalanced case. We have now tuned to marker N2, the fundamental series resonant mode in the balanced state, and that means that we can now try applying some power. So we're going to apply power just from the exciter at this stage, and we're going to be using the SWR meter to look at and tune the match between the linear amplifier and the experiment. So I've got this in balanced already. I'm not going to use the linear amplifier at this stage, just the output from the exciter, and we're going to work with up to about 120 watts. And first of all, I will just wind this up so you can see what I was doing a little bit, and then I will focus in on this area so we can see more specifically about the tuning. Okay, so we are minimum power, we are on air, this is off air. This is basically on. Now we're not actually, although we're working in the amateur band or close to the 160 meter amateur band, we're not actually going to be transmitting anything here. We're not connected to a radiating aerial, which is outside. So therefore, we're not causing interference to adjacent bands. We are keeping the power entirely encapsulated within the experiment that we're working with here, and we'll see that's the case as we start to transfer power into the load. So turn the exciter on, power's fully wound down, I'm on balanced output going to the experiment, and first of all I could try my power out down into the dummy load just to make sure that that connection is working. So I'm going to wind up until I get some power coming out. Here we are. We can see the needles going up on a dummy load. Everything's coming up here. So I'm going to set about 20 watts. So it's about 20 watts, SWR of 1. We're in a perfect match because we're in match with a 50 ohm. There's nothing coming through the linear amplifier. That's on standby. This has come up as well. Has it come up? Yes, it has, and there's nothing reflected. So we're just putting to the dummy load. I can go up from there. My SWR is fine. There's nothing for me to tune. I've come up to 50 watts. Let me just check down here. Yeah, that's almost on 50 watts. And ISWR is still 1. I can go up further to the maximum of this amplifier, the exciter. It's about 121 watts, matches about 1.05 SWR. The power meters come right up. So everything's working fine with the exciter into the dummy load, and it's matched in the way that we would expect it to be. Let's just put that onto the 300. That was why I wasn't sure where that was. It needs to be on the 300 watt range because we're working with the exciter and not with the linear amplifier. Okay, so now I'm going to switch over to the experiment, and I'm going to also zoom the camera in to this region. All I'm adjusting here, I'm keeping the frequency locked so it doesn't change, and I'm adjusting the carrier output in CW mode, so we're just putting a sine wave in. So let me just adjust the camera. So we can see what's going on. So now we get, I'll keep this in the picture as well. Just turn that slightly. So, okay, so now we've got the SWR and watt meter, we've got the antenna tuner, all the bits that I'm going to be using here, and we've got the bird power meter in the screen. So what I'm now going to do is I'm going to wind up. Let me just turn it off first of all. This has got this actually where it stopped sampling. It's just left with what was there last. So if I now turn the exciter back on, I'm going to wind up until we get just a small amount of power. There we are. It's about 5 watts, 10. About 10 watts of power. About 9.9. About 10 watts of power we can see. The SWR is 1.84. I can see just a tiny glow on the bulbs in the experiment. I'll bring the camera back out so we can see that. And I'm going to first of all tune to minimise that SWR. So I'm looking for this bar here to be as low as possible. 1.79, going up again, just tuning the input until its minimum point. Then I'm going to tune the output. We'll just check the inductor position. Yeah. About there was minimum. It's 1.59 now. Just keep tuning it until we can get it as low as possible. 1.5. Or there, right down. 1.29. 1.2. There. 1.0. 12.2 watts power. Okay, good. Perfect match. 2.2 megacycles. I'm going to come up in power. Now, you see the SWR is going up to 50 watts of power. I generally like to keep the SWR 1.6. I like to keep the SWR below 2 if I can. We're just going to adjust a bit more. Oh, very good. There we are. Slight adjustment now brought us to 1.0, 51.6 watts. The lamps are starting to be well lit. We'll take a look at that in a minute. So I'm going to go upwards from there. Now I'm up at my 120 watts of power. Adjust. Pretty good. There. So 120 watts of power, SWR of 1. And the bulbs are lit, which I'm just going to pan out now and show how that looks on the experiment. Right, let me just pan that back around a little bit. There you see, it's just slightly there. Okay, so we see that the lamps are brightly lit on the experiment. Obviously they're not lit evenly because we have these ones are brighter than these ones because we don't have a reciprocal cavity. The cavity here, the open circuit, and the open circuit of course at the top end, the cavity formed through the coil and through the single wire extension is not reciprocal and evenly balanced. So obviously we don't see the illumination of that load in a balanced way, which we would see when we put it into a TMT. Okay, so I'm going to wind back down. So let me just tune. I'm just adjusting the SWR again up to 1. It drifted slightly. And now I'm going to turn the exciter off. Turn it back on. SWR is 1 still, 120 watts. I'm going to wind back down to 50. SWR now stays good. And we see there's plenty of 50 watts. Bulbs are still illuminated. SWR is 1.09. I could adjust that slightly. And I'm just going to have a little frequency test here. I just want to go in either side. You can see that we are actually at the peak of that performance. I'm just making small adjustments of frequency at 50 watts, keeping an eye on the SWR as well. Make sure it doesn't go too high. 1.5 there. You see we go through a peak. Maximum illumination where we were at 2.2 megacycles. So I just made small adjustments to the frequency just to make sure we were really at the optimum point whilst I was watching the SWR. And you saw the SWR went up to about, if you can see that, up to about 1.5 either side. So provided I can make small adjustments of frequency, provided I'm keeping an eye on that SWR and keeping it less than 2. So winding up further from there, go right back up to 120 watts. Just adjusting the SWR again down to 121 watts, and those bulbs are very well illuminated. I mean, there's more than enough that we could do experiments with just the exciter on its own, without even using the linear amplifier. I'm just going to adjust the camera slightly, put it in the picture. There's an awful lot of experimentation one could just do with a transceiver, 120 watt transceiver, with an antenna tuner, an SWR meter onto your experiment. And that's just 100 watts. We haven't even involved the linear amplifier in this yet. Turn off, turn back on. We can now see also power represented here going through the antenna tuner. This is the forward power, this needle is the reverse power. Stable. Slight adjustment there, down to 1. There we are. So we are tuned now to optimum position. We're driving this system at the series fundamental resonant mode. We can see that the neon lamp has come up bright here. showing that we've got good tension at the top end. And the single wire load, that's 100 watt single wire load, is well illuminated. Obviously it's not reciprocally illuminated, it's not balancedly illuminated across the two half sections of the bulb because of the cavity imbalance. Okay, so we could do experiments with this. We could easily do experiments with this. For example, let me have a look at the tension at the top. Yeah, we have a good tension there. And that's just with 100. That's just with 100 watts of power. Okay. So what I'm going to do now is I'm going to pan the camera. I'm going to move the camera position around so that we can see the experiment as a whole, and then we're going to look at some of the TMT. I'm going to be tuning in a similar way that I just showed with the linear amplifier, but I'm going to be focusing the camera on looking at the experiment so we can see what's going on. Okay, so I've readjusted the position of the camera, so we've got the complete experiment in now. We can see the transmitter coil, the receiver coil, the two Bird through-line watt meters, and the two incandescent bulbs at the far end. And I've repositioned the loads that we currently had in the single wire transmission medium in the middle, but I haven't connected it at this end yet. So it's disconnected here. And I'm going to do that for a reason. So I'm just going to turn on the transceiver again. I haven't readjusted. I'm actually going to turn down the power, turn it on. I'm going to wind the power up, checking the SWR as we go. There's come on. Just going to have a slight readjustment of the SWR. I'm going to wind that all the way up. Okay, so that's just adjusting the SWR to minimise that. .1, 1.05, 1 at 119 watts output. Right, so the reason for doing this is, let me just turn it off again, make sure our point's stable, turn it back on. Yeah, so SWR 120 watts. Now, this is illuminated from here. It's not connected here. There is no tension here. There is power coming in. There is no power coming out. So what this shows us a very important thing. It shows us that these transmit and receive coils are not coupled. They're not magnetically coupled with each other for a normal transformer. The magnetic field falls off as R cubed as they go apart. These two transmit and receive coils are positioned around about 2.5 times their diameter. So above 2 is in the close midfield region, so they are not influencing each other by magnetic transformer coupling in the normal way. They are actually not impacting on each other in that respect. And even when I put the single wire transmission medium all the way close over to the receiver, it makes no difference. It's not connected to the system. And the point to illustrate here is that the coupling between this TMC system comes as a result of the single wire transmission medium. So by putting the single wire transmission medium and coupling that up to the receiver, we do have an interactive system between the transmitter and the receiver. We could imagine, obviously, that single wire transmission medium might be a telluric channel, for example. So if we were connecting both of them into the earth, and we had them much more further separated from each other, we would be looking at the telluric transference of electric power. And we're going to be coming on to that in another post. But the illustration here, or the first part of the experiment, is to show that these coils are outside of the distance where they are magnetically coupled by the magnetic field of induction directly. So I'm going to wind that down now. Turn off the exciter. I'm going to reconnect this to make it into a TMT system. And now we're going to bring it up slowly, obviously retuning. I don't have the load connected. The 500 watts load is not connected at the end at the moment. We're just working with the TMT system itself. So I've wound the exciter down. I'm going to turn on. I'm going to bring it up to 20 watts of power. Okay, so now we've got very high SWR. You would expect to 18.3, because now we've changed the tuning of this system. We can see a very, very slight glow, but I'm going to, first of all, I'm going to work on bringing that SWR right down. It's already at 5. I'm retuning the antenna tuner, like 1.8. Adjusting the inductor as well to find the best point. Right, so I'm having difficulty actually tuning there. Below about 2. About 2.1. Having difficulty tuning that. I'm going to bring the power up slightly, because sometimes trying to tune at too lower power actually makes it harder. So I brought it up to about 20 watts. That's fine for the exciter. We don't even have the linear amplifier in there yet. Now I can get it down to about 1.48 now. That's better. 1.38. About the best so far. Adjust the inductor a little. That seems about in an optimal position. 1.4. I don't seem to be able to get it any lower than 1.4 at the moment. We can see that the bulbs are illuminated. Oh, no, 1.3. 1.14. 1. 20 watts. Okay, I was able to. Now we're also going to have a check on frequency. I've just unlocked the frequency, and I'm going to be looking to maximise that single wire load to make sure that we're still in the right driving point. Yes, that hasn't really changed a lot. I'm going to leave it at 2.2 megacycles. Okay, so 21.7 watts. Going to increase power. It's 80 watts. 120, so that's full. We can now see that there's a balance. There is a much better balance in the illumination. SWR is 1, power is 120 watts. All of that power, or most of that power, is being dissipated in the single wire bulbs. We see we're not illuminated here, but we are here. So basically we are in an imbalanced situation. And to do that, I need to look at the tuning between the parallel points and make sure that that's all tuned properly. So if I wind it down, I'm going to take out this load, the centre here. We're just going to connect them together so we have the two sides. Okay, I just check the balance of the two tuning capacitors each end, and they are actually in the right place. They were in almost exactly the right place. I just did some very fine adjustment just to balance the parallel modes from the two sides. Now I'm going to do a tuning check to see how or if the resonant frequencies corresponds with where I would expect. I can put that this way now in the picture. So I'm at 2.22 at the moment. I'm going to turn the exciter on. We're at low frequency. See, we're in a little bit unstable. I'm going to move. Have a look at where we've got these peaks again. That's a strong 2.17. We shifted slightly, we were at 2.2 before. Keep going up. Let's have a look for the upper parallel. There it is. Shifted slightly. Okay, so we're just going to retune slightly now. If I look at the balance characteristics, around about 2.22 from Z11, a little bit of shift from there. We're going to go up to where this is maximum and stable. So I'm going to shift it down to around about 2.17. I think we'll be fine. Lock it there, 2.17. Okay, so there we've got maximum, it's 2.17. Take that off. And now, so at this stage, I think I'm going to bring the linear amplifier in. I'm going to keep that out now. I'm just going to put the load on the end here. Bring the linear amplifier in so we can tune up the TMT fully, including, so we've got one 500 watt bulb connected, going through coming off the output of the bird. And we're going to go through the same tuning, turn on the exciter. I'm going to first of all tune the linear amplifier up. So to do that, let me just bring the camera back into view. Okay, what I'm going to do now is I'm going to start using the linear amplifier, and first of all I'm going to tune it up to the dummy load. So the exciter is off, turned down. I'm going to select the dummy load here. I'm going to switch this over to operate. When I turn on, okay, the exciter is on at minimum power. The linear amplifier has come on, there's no output yet. So we're going to bring ourselves up a bit, bring some power up, about 20 watts. Quite like 20 watts as a tune. We are getting some grid current and we're getting some plate current. And now I'm going to adjust this process. Normally you would dip the grid or maximise the RF output, whichever you prefer. I'm going to bring it up a bit more. We ultimately want to get, let's have a look, 500, so it's about 100 watts. Just adjust the linear amplifier, just to maximise. Out there, we're maximising the power out there. Yeah, let's pull back the load slightly to about there. Okay, let's put this on the high range. We can push up a bit. Okay, grid current's okay, plate current's up at 0.6. We're pushing about 300, 400 watts. Just going to check that set up. Ultimately, we want to get the linear amplifier up to where we're going to plan to use it. 400, 500, up about 500 watts there. Grid current's about 200, plate current's about 750. It's about right there. Let's go up a range. Yeah, about there. Okay. Alright, so that's a reasonable linear amplifier, it's reasonably tuned. We're going to move back over to the experiment now, and I'm going to move the camera back into its position so we can see the experiment. Okay, I've repositioned the camera. So now we're using the linear amplifier. We're going to tune up now. I've switched it back over to the balance mode, and we're going to tune up against the experiment. We've taken the transmission medium load out, and we're just using the 500 watt load at the end. So we turn on the linear amplifier system. We're going to wind up to about 20 watts. Very high SWR. We're going to adjust that. Bring it back down. Okay, bringing the SWR right down to 1 and 40 watts output. Yep. We look a pretty good tune there. 40 watts. You can see there's a tiny glow on the output bar. I'm going to bring it up to 100 watts. SWR's gone up to 1.4. We can see the glow at the bulb at the far end. Receiver load. Just bring the SWR down again. Careful bit of tuning. There we are, 120 watts. So we can see that. We can see now the illumination of the bulb at the end. We can see we've got tension here and here. The neons are both lit. We're going to go up a bit further. About 250 watts now. Get the SWR tuned up. Some more power. 400. SWR tuned. 1.4. 06, very good tune. Might be able to get it even slightly better. Put up to this a bit. One. 350 watts. I'm going to keep going up to about 500 watts. So there we are. SWR1, 500. Just over 500 watts coming out of the linear amplifier. That's good tension at the top. It's equal. We can see that our incandescent load is fully lit, and on the bird meter we are showing 500 watts. 480. A bit of tuning. Let's keep SWR1. Running stably. 500 watts. That bulb is fully illuminated. We are reading 480. 500. So, running currently at 96% transference of electric power, and 96% efficiency of that energy is being transmitted through that single wire transmission medium. Now we can probably get that up a little further by some careful tuning. We're putting about 530 watts out of the linear amplifier. We'll just adjust the linear amplifier tune a little bit as well. Just peak the power output there. That'll help us to keep the grid current down. Okay. So we've just let the system cool down a little. We're going to turn back on again. Back up at around 500 watts. And we'll just have a look at the tension in the circuit. Through the null, high, null, high, null, high, null, high. We can see those, the null in the centre there, characteristic of the LND mode in the single wire transmission medium. So high tension, down to the null, back up. The null is very sensitive. There's illuminated, illuminated, null in the middle, illuminated, illuminated, back up, high tension there. It's good. So another interesting, we were looking at the modes, or the null point in the centre. It's just having a quick look at that with the fluorescent. The thing about the fluorescent is that it's diffuse. You can see the null very easily. The centre there between the two, right in the middle between the two, where we would expect it to be. Because it's diffuse, we can't see any more detail about what's going on in a single wire, because it's a diffuse light source. If we put an ultraviolet lamp there, modes that are going on, especially if I turn down the power, you start to see the bit so that we can see the areas of high and low. Tune. Good. Just get them still. Another good way of looking at the LND mode. I can see that looks like it is coming out in the camera. There's another characteristic of the LND mode is that there is a changing phase relationship between voltage and current in the single wire transmission medium. Now in a transverse case, you would expect the impedance along that single wire to be constant. I mean, it's only a 2 meter wire connecting both sides, and in the transverse case the voltage and current phase relationship would remain stable. But what you actually measure in the single wire transmission medium is that the phase relationship between voltage and currents they actually change along the wire, and that's another characteristic way to measure the LND mode. And the good thing about using an ultraviolet bulb is that you don't get the diffuse characteristics that you do with the fluorescent bulb. .500 watts going in, 525 going into the antenna tuner, 25 watts being lost in the balun, 440 on this side. A little bit of tuning. Yeah, SWR need a little bit of tuning. Brings back up to maximum power. 500 watts, out to 440 still. Might just try tweaking the frequency slightly to see if we can find some improvement in efficiency. Just small tweaks. It's almost 500. Let's just bring it back a little bit. Okay, I've just been doing some tuning work. I've adjusted the exciter frequency just slightly, bring it closer to the amateur radio band, the 160 meter band, so I've adjusted to 2.08. I've been looking for the optimum efficiency. It takes quite a while, just very, very small adjustments to all of the tuning. So I've gotten to an optimum point now, and we're going to take a measurement of that. So I'm going to put the exciter on. We're at 2.08 megacycles. We have got an SWR of 1. I've optimised the linear amplifier output. I'm just checking that. Yeah, optimised the linear amplifier output. SWR of 1. And I'm going to take a reading, an efficiency reading. Set my input at about 500. I've got 510, 505. What's that? So 505 divided by 510. That's 99. 99%. Let's take that reading again. It's just drifted slightly. 520. 515. 515 divided by 520. 99%. We'll take it again. Stable. Ah, it's very close. Very close. Might get the camera in so we can have a better look at those. 530 at the input, and I made that 520. Just check that again. Yeah, 530, just under actually. Straight on, it's about 525. That's 520. 520 and 525. And that 520 divided by 525, 99%. 99.1. 25 divided by 530. 520 divided by 525. 99, yeah, 99.4 or 5 actually if you round it. 99.5. Just going to pan that back round so we can see the other one. That's where you could do with two cameras, one on one, one on the other. Difficult because we're in maximum zoom here. So settle in there. What does that read? 525. Yeah. 525 and 520. 99.5% efficiency in the transference of electric power down a single wire transmission medium, lighting a 500 watt bulb. That's good. Just pan out from there. There we are. That's panned out. We can see that the swing that round a little bit more, not getting in the way. We can have a look at our setup here. So we can see the exciter sitting at 2.08 megacycles. That was where I could find the best efficiency for the transference of electric power. Just tweaking, we were running at 2.17 before, and I couldn't get it up above 90%. So I readjusted, just tweaking the frequency a little bit, adjusting, retuning the SWR. That's one again, it's 1.02. Grid current's about 150, plate current's about half an amp. Forward power coming out of the linear amplifier, it's about 580 watts. We're putting, I think still is at 525 and 520. So we're stably sitting at 99.5%. transference of electric power in that single wire system. That's great. Really great. Nothing's overheating. Everything's running within capability. Good. So I'm going to go pan this back round to the experiment because we're going to try another experiment. Just pan that out. Not in. Out so we can see the whole experiment again. There we are. I'm just going to turn that off and I'm going to add, take that load away. I'm going to add a second bulb. Okay, so we've got both bulbs in now. Going to run that. Obviously our SWR will probably be higher, which it is, it's up at 2. I'm just going to tune that down. There we are, just a small tuning down to 1.02, 1. Tuning the amplifier as well, loading. Loading's changed. And there we are. Grid currents come up considerably, almost up to 200. Interestingly, our efficiency really has dropped off. We are putting 800 watts in and only getting just over 500 out. Look at our efficiency drop there by doubling that load. We've changed the conditions quite considerably. Just tuning, see if it makes a difference. Grid current there, just knock that back to about 200. Not too much grid current in. Keep that down. Now we're lighting 2 500 watt bulbs, much lower efficiency once we added that in and retuned. Much lower efficiency. And we kind of hit the optimum just with the single load. Let's go back to that. We'll check our measurements. SWR needs to be adjusted again. Just get that a bit down so we minimise our reflecting power. There we go. Pushing rather a lot of current, grid current's quite high, so I'm just going to pull that back down a bit. 500, 495. So 500 watts in, about 550 coming out of the linear amplifier into the tenor tuner, 50 watts left lost in the balun, 500 into the and 490 out. So we'll just check that efficiency again. 98%. We just retune a little bit again. We just retune a little bit again, so we look at that. 495 by 500, 99%. There we go. Back to 99%, 2.08 megacycles. SWR 1 more check. 500, 495, 99%. Transference of electric power. So what we're going to do now is I want to make a demonstration which shows the effectiveness of the single wire transmission line. So I'm going to turn off and I'm going to insert into the single wire transmission line this hairline wire that I have. Let me just set this up and then I'll explain what it is. Careful, it's very delicate. Get it set up there. There we are. Right. So what I've done is I've put a 40 AWG, that's an 80 micron wire, 0.08 millimeters. It's the same thickness approximately as a human hair, stemming from here to here. Let me just check how long that is. 60 centimeters. So it's a 60 centimeter 40 AWG copper wire. As the single wire transmission medium. Now, let me see, you won't be able to see that. Let me see if I can focus in and we can actually see that wire on the camera. I don't know whether it would be possible. Bring in one of the clips. Yeah. I think you can just see the wire there. Let me bring it back to the clip. Yeah, there it is. There's the wire. Goes across. All the way. There's the wire. There, into the end. So we can see the wire just here. See the reflection from it. That's a 40 AWG wire. Go back across all the way to there. Great. Okay, so that's the wire. Let me just zoom out. Fully, so we see the experiment. So we have a 40 AWG wire, 80 microns, 0.08 millimeters, and we're going to see how much power we can transfer down that. That wire is thinner than a fuse wire. I've got the exciter turned down. I'm going to turn on. I'm going to wind up, being careful. We might have to readjust the SWR to bring up to 100 watts first. Okay, we can see there the system is on. we've lighted a little bit. We're putting out, yeah, about 100 watts. What we're getting at the other end, just under 100 watts. SWR is 1.6, so we're not going to take an efficiency measurement yet. We're going to go up in power. 500 watts in. So 510 in. 510 out. Incredible. That would be 100%. The meters probably couldn't quite measure it that accurately. Let me try and get it on 500 here. Just a very small change. We just use the linear amp to adjust that slightly. 500. 5. I can't tell the difference. 500. 100%. It's probably 99.9. 99.9%. 500 watts with an 80 micron 80 micron wire. Human hair. The thickness of a human hair, 60 centimetres long. We are doing transference of electric power at more than 99.9% efficiency. And we could do that. What this demonstration is good for is it shows that the magnetic and the dielectric fields of induction are around the wire. That transference of electric power is happening through those fields between the transmitter and the receiver antenna, and they are not travelling through the wire. They are in a region around the wire. The wire is simply acting as a guide. It is guiding the dielectric and the magnetic fields of induction from one end to the other. It is not passing through. So we would expect the efficiency to go up as the wire becomes smaller. Let's just check. We're up to 538. 538. We would expect that efficiency to increase, but it's still incredible. 540 watts of power being passed down, and we're not even running at full power for the linear amplifier. If I were to go up further, almost 600. Yeah, almost 600 watts going down that single wire. Push it up a little bit even. It's about the max of this tuning. Overstress it, bring it back to about 500. Also 500. Along that single wire. There's a great demonstration, I think, of the magnetic and dielectric fields of induction. Between the transmitter and the receiver. We spend a lot of time tuning to get the coupled energy in from the primary to the secondary. Longitudinal mode connects the transmitter and the receiver. That's tuned as well. They're both tuned through those three fundamental modes that are in the Tesla coil. Nice analog shift there. No in the middle. highest efficiency. 510. About 508, 509. What would that be? Let's call it 508. 99.6. So more than 99.5% efficiency in the transference of electric power. 2.08 megacycles through an 80 micron, 60 centimetre single wire transmission medium. That's great. This is really exciting experiments. We just checked for stability. We're going to turn it off. We're going to let all of those come back down. Turn back on without retuning. We take another measurement. 520. 518. 518 divided by 520. 99.6%. Incredible. And it's sustained. Grid current about 150. 500 milliamps plate current. SWR of 1. It's nice and stable, balanced. Great. Well, this is high efficiency in transference of electric power using a linear amplifier generator. Great.